So if we have a higher order differential equation, and let's simplify that as x double dot plus ax dot plus bx, and for the time being let's assume these systems are without an input. Like I said earlier, if you have a first order equation, we'll have one input. If we have a second order equation, then we typically have need to pinpoint the entire solution. We need two initial conditions, right? So how do we handle it? Well, of course, there are techniques that directly handle second order equations. However, I'm going to show you a technique called state space transformation, where every higher order equation, linear or nonlinear or time varying or otherwise, we can change them into a first order differential equation of the same kind. Meaning, if the higher order equation is LTI, then the higher order equation will remain LTI. LTV will go to LTV, and so on and so forth. Nonlinear will remain nonlinear. If it is time invariant, it will remain time invariant. And the technique is quite straightforward. In this particular case, we have a second order equation, so it becomes a state space of two variables. Okay, that's the term we use. So I'll define these state variables as y1 is equal to x and y2 as x dot. So I'll repeat the technique. Basically, for a second order differential equation, what we do is define two variables and choose them as x and x dot. This is not the only choice, but this is the standard choice and the easiest choice that one can do. And the next thing is basically we have to rewrite every part of the second order differential equation in terms of y1. So in the final thing, we should not see anything but just the constants a, b, x0 and x dot 0, which are the initial conditions. So, and then the standard choice will make us always take the derivative of these two variables, y1 and y2. So y1 dot, as we know, is x dot, but we don't want to see x anywhere. So, but x dot is y2, so y1 dot is equal to y2. So that's the first state variable equation. Y1 is the first state variable, and then y1 dot equals y2 is the first state variable equation. And of course, we see that x of 0 is x0, but x is y1. So we can write that as y1 of 0 as y0, sorry, x0. So now if I take the derivative of y2, then that is nothing but derivative of x dot, which is x double dot. Remember, again, the technique demands us to write everything in terms of y1 and y2. So how do we eliminate x double dot? Well, that's where we have to suddenly remember that we have a second order differential equation in terms of x double dot, right? But x double dot, if you look at the equation, is nothing but minus ax dot minus bx. And using the fact that x dot is y2 and x is y1, I essentially get y2 dot is equal to minus by1 minus ay2. And of course, the second initial condition, which is x2 dot is equal to x dot 0, is going to be y2 of 0 is equal to x0. Now, interesting thing is, after we transform this, if they're all linear, as in this particular case, we can put them in a nice vectorial fashion. And that will give us y1 dot, y2 dot as a vector is equal to a matrix, we will see in a second, times y1 and y2 with the two initial conditions we already have written in the form of vectors. And you can clearly see y1 dot is y2, so the matrix will be 0 and 1, the first row of the matrix, and the second row of the matrix will be minus b minus a. So this is called, like I said, state space transformation. Yeah, so this works every time. Even if it is nonlinear second order differential equations, we can do the same. If it is a third order differential equation, we have to pick 3 variables. Suppose we had two coupled equations. One is second order differential equation and the other one is third order differential equation. Then we have to pick 5 variables corresponding to both of them put together. 2 plus 3 is equal to 5, and we will get a 5 state variables resulting in first order vector differential equation of dimension 5. If it happens to be linear, then basically we will always end up with things like this. The matrix that you see here, here it happens to be a second order equation, whereas the case where we have one second order and one third order could be coupled, we'll get one single fifth or first order, but a vector differential equation of 5 states or 5 dimensions. And this is a very important technique. Like I said, even if it is time varying system, we can do this transformation. Even if it is nonlinear, we can do it. And the character, if it is time invariant, it will remain time invariant. If it is linear, it will remain time linear, right, in the state space transformation. Once again, I want to kind of go through this technique, and we won't really get into this again ever in the class beyond using this technique on and off in various examples. What did we do? We have a second order differential equation. So first thing we need to recognize is second order higher order differential equation can be converted into state space equation of 2 variables. So we pick some 2 variables. In this particular example, we call them as y1, y2, and define them to be x and x dot. There are other ways of doing it. You can imagine, you can try, you can experiment on your own to see what are the other possibilities of defining these state space variables. But the standard one is basically we pick the first one to be x, the second one to be x dot, and the next part of the process is simply take derivatives of each of these state variables. When we take the derivatives, eventually the goal is to eliminate the original variables of x in this particular case, or x dot or x double dot, and rewrite everything in terms of the state variables except any of the constants. What are the constants? In this particular case, the a and b, the coefficients of the differential equation, and the initial condition x sub 0 and x dot sub 0. They are the loosely speaking position and velocity inputs that we have, right? So after doing all this, we can write, if it is linear, write everything in terms of a matrix form, right? So this is a very powerful technique, and this allows us to therefore pretty much with first order equations, whether they are linear or nonlinear, right? So if I am giving only importance to first order equations, you see the reason now, because of the state space transformation technique. So before we go into LTI models, with input, we will first specialize them to the case where we don't have any input. And let's remind ourselves, for this equation to be valid, x has to be Rn, x dot is therefore Rn, x0 is Rn, A has to be square matrix of dimension n by n. So in the scalar case, we had this magic trick that we did by multiplying e power 8t, e power minus 8t specifically. Now in the matrix case, if we had a same concept as exponential function, then we can exactly do the same thing, right? If the derivatives work in the same manner as scalars, then we would end up with same answers, right? So, and In the scalar case e power at, the reciprocal of that is e power minus at. In the matrix case, the equivalent of the concept of reciprocal is inverse, and if e power at is the inverse of e power minus at, then we will end up with exactly this identical expression, except the meaning of that expression is very different perhaps. So we will look at this carefully now. So there is some concept called matrix exponential, and it's not surprising that basically the definition of matrix exponential is again identical, except in the scalar case we could actually think of it as a inverse of a logarithmic function, whereas in the matrix case we actually directly use the series expansion of e power a or exponential of a as identity plus a plus half a square plus 1/3 a cube. Sorry, there's a typo, 1/3 factorial a cube and so on and so forth. So, a lot of questions come into picture, whether this particular expression is bounded and whatnot and things like that. Luckily, all of them can be proven to be well defined and so on. One of the simplest things that we can do is substitute 0 matrix for A, the square matrix 0, and we can see basically every term from A onwards will be set to 0, and then we'll simply get identity. But more interestingly, if we put actually instead of A, if we put a diagonal matrix instead of A, one can imagine basically we'll end up with another diagonal matrix, which we can call it as e power d, is also diagonal with elements of exponential of in each of the diagonal terms. Right? These are quite important properties that we will use in a minute or so. Another fairly obvious property is a times e power a is going to be equal to e power a times a. So that means matrix exponential commutes with its matrix, and similarly, using this formula e power d is equal to diag of this thing, we can see that e power identity is actually scalar e times the identity. Where does it lead to? All these things lead? Well, if A happens to be some complicated matrix, then computing e power a is therefore complicated. And therefore, one technique that one can use is diagonalize it or do a similarity transformation. So, A is equal to SB times S inverse, then e power a is equal to S times e power b times S inverse. Okay. How do I know this? We can simply basically substitute A in this expression and we get all these expressions simplified in this particular expression. E power a times is equal to S times e power b times S inverse. Right. In the case of diagonalizable matrices, essentially what that means is if we know how to find this S and b times and S inverse, we can simply find e power a by using this formula. Yeah. So if A and B commute, then the standard formula of e power a plus b is equal to e power a times e power b, which is also equal to e power b times e power a, will be satisfied. Right. This is a obvious thing in scalars. Well, not so obvious, but this is something well known in scalars. But in the matrix case, it's only true if A times B is equal to B times A, and in fact, the result goes both ways. If they do not commute, then we don't have the equality. Another very important and interesting property is determinant of e power a happens to be exponential of the trace of a. Trace of a, if you recall, basically it's the summation of all the diagonal terms. So this essentially shows that determinant of e power a is never going to be 0, because that's equal to the e power some number, and e power some number is never 0. And one can easily show using all these properties, e power a, inverse of e power a is equal to e power minus a, right? And I'll leave it as an exercise why it is easy. It's not easy if we actually use the expression that is given by the series, but it is quite straightforward if you use all the properties that we see on this page. So what else is true about this particular matrix exponential? Well, if we take the function, matrix exponential of a times t, where t is the scalar time, if you take the derivative of e power at with respect to t, in the scalar case, we know that it is nothing but a times e power at, so it remains the same. But of course, in the matrix case, we have to be careful about the order of multiplication. But fortunately, they commute because a commutes with a, and so on and so forth. That gives us this identity d power dt. D by dt of e power at is equal to a times e power at, and we use this very often, and that's quite important. So let's look at an example where we compute this matrix exponential, and we will take a very specific example of a equals this 0 1 0 0 2 by 2 matrix. And if you sit down and compute a square, that is multiply this matrix by itself, you will get 0. It's a very special matrix called nilpotent matrix. In general, a nilpotent matrix is nothing but if you take A and multiply it some finite number of times, whether it could be 2, 3, 4, whatever number of times, if you get 0, then that's called a nilpotent matrix. So this matrix is nilpotent of order 2 because when you multiply it just twice, you get 0. And you can substitute the fact that a square is equal to 0, a cube will be 0, and so on and so forth, and just use that particular fact. E power a is going to be equal to I2 plus identity plus a. And in general, if a is nilpotent, then like I said, for some k, a power k is equal to 0, and essentially after that a power k term, everything is going to be 0, and e power a becomes a finite series, and you can actually simply compute the finite number of expressions. But on the other hand, if we have a general matrix, it's not so easy. So one particular example is basically if it is diagonalizable, then we can compute it as e power a is equal to s times this diagonal matrix that we have seen before times S inverse. So that's still a very special class. Nilpotent matrices are very special, but diagonalizable matrices are special. But in general, there is something called Jordan decomposition. If you're not aware of it, you should Google it, and it will look similar to your diagonalization. So Jordan decomposition says that every square matrix can be written as S times J times S inverse, where J is actually something that has Jordan form, and typically that can be written as a diagonal matrix plus a nilpotent matrix. And the details are quite interesting, but we don't have time to go through some of these details. So, but we know how to compute matrix exponential of D, a diagonal matrix, and matrix exponential of a nilpotent matrix. Now, combining these two will give us a general method to compute matrix exponential. Invariably, we don't want to compute matrix exponential unless we are doing a numerical problem. But in general, we like to understand the nature of these matrix exponentials, especially when there is time involved, and that's what we're going to see. How this helps us solve ODEs of vector form. We have already seen, in fact, before even introducing the matrix exponential, we have seen how it works for the case where there is no input. Here we look at the case where we have the input. Here we assume that the U is of dimension Rm, it's a real vector of m dimensions, and therefore B has to be n by m matrix. So again, we have seen this multiple times, but we understand what it means to be e power at as a matrix. Here I write greater than 0. Actually, what that means is it's a positive definite matrix. That's not necessarily the case. It is actually a typo. What I meant to write is actually, since e power at is invertible, right? So ignore this particular thing that says greater than 0. So, but just as before, we can write this ODE by multiplying e power minus at on both sides, and we get this expression which looks identical to the scalar case and no different from the scalar case. D by dt of this e power minus at times x of t remember d power dt of e power at or its inverse e power minus at is very similar to the expression that we have in scalars, except in matrices we are safe because they all commute. So again, the same standard method, basically by integrating everything we will get this identical looking expression, x of t is equal to e power at times x0 plus 0 to t integral e power at t minus tau b times u tau d tau. Like I said, this expression in the integral is known as a convolution between two functions. Only warning that I would like to give in this particular case is ensure that the order of the matrices, the way it is written here, should not be disturbed, because these are matrices. We cannot interchange the order just like that. But beyond that, they are very similar to scalars and fairly straightforward to understand if we understood the scalar. The only, of course, difference is matrix exponential is defined for the matrices. So clearly all LTM models, whether they are scalars or vectors, have a clear solution. Even if we have higher order differential equations, we can convert them through state space transformation and bring them into a vector form so that we can solve that particular problem. So therefore, since we have a closed form expression for the solution of LTI models, we can solve the problem, I mean, we can use the solution to say many things. So therefore, people love linear models because we can say pretty much everything. And specifically LTI models have complete closed form solution, and whatever we want. If we want to control a system just by designing a particular u of t to give a very desirable x of t, we can try to do that, right? But in the case where we don't have that simplicity, we are pretty much lost, and this course is about showing few techniques where we can understand through different methods, not always looking at the solution. So the next thing I want to look at is just a small extension, or make one point regarding linear time varying models. Linear time varying models without input in this particular case, you can see x dot of t is equal to a of t times x of t. So no difference between the linear time invariant and this one, except a is now time dependent. A is a function of time. And I'm going to use this trick by defining some tau is equal to t minus t0, and defining these two variables x1 and x2 as given by x of t and t respectively. The linear time varying model now can be written as this two first order equations that look time invariant. In fact, they are indeed time invariant models. So we have x1 dot of tau is equal to a times x of 2 of tau times x1 of tau with some initial condition, and the second one is x2 dot of tau is equal to 1. So what did we do here? We essentially transformed a time varying, though linear model, into a nonlinear time invariant model. Where is the nonlinearity here? A is a function of x of 2 here, which is a nonlinear function typically, but then otherwise this is a linear time invariant model. So there are important points that we observe based on this particular transformation. So every time varying model, linear or nonlinear, can be transformed into a time invariant model with one additional dimension. But a more important observation is, even if you have a linear time varying models, the linearity is sort of fooling us. It's hiding behind a disguise, so to speak, and in that sense linear time varying models are indeed nonlinear models. So that's why it's almost impossible to do a good job in terms of finding solutions. There are expressions that we can write for time varying models and things like that, but almost impossible to do beyond much beyond that. So therefore, as far as we are concerned, we treat linear time varying models as part of nonlinear theory. Even that we don't consider, because that's sort of next level of complexity. But we restrict ourselves to time invariant models, linear and nonlinear kind, right? but linear kind is quite simple, because we have an X-based solution. So all this, something that's fairly obvious, is basically, unfortunately, if we have a nonlinear time invariant models, even though they are time invariant, we don't have closed form expressions, and obviously the more complex case of nonlinear time varying models also will not have closed form expressions. And like I said, you can convert NLTV, or the nonlinear time varying models, as an NLTI with adding one dimension, just like we did for the linear case, and therefore we restrict ourselves to essentially nonlinear time invariant models. So that brings us to the end of lecture 2. Lecture 3 will focus primarily on nonlinear side of ordinary differential equations. We have seen how linear models are quite straightforward. They are still complicated, but the fact that we have a solution, we have a way to work towards those models. We can actually put them in the computer. We can do a lot of things, right? So that's what we are looking forward. Thank you.